This is question number 12 from chapter 16. It says particles of charge positive 75, positive 48, and negative 85 microcoulombs are placed in a line. The center one is 35 centimeters or 0.35 meters from each of the others. Calculate the net force on each charge due to the other two. This involves using Coulomb's law and recognizing that you need to add and subtract these forces based on their directions. I'm going to start by first identifying these numbers. I'm going to call this charge right here charge number 1, the one in the middle charge number 2, and the one on the right-hand side charge number 3. And I'll recognize that the net force on charge number 1 is going to be equal to the charge interactions from the interactions between 1 and 2, which we'll recognize this is going to be to the left or negative. Oops, didn't mean to do that. Negative, and the force due to the charge interactions between 2 and 3 are going to be positive. Let me go ahead and restate how we know that. Let's first of all remember that the force on charge number 1 is going to be to the left or repulsive. This is going to be F12. So I got to remember that anything to the left is going to be negative. So therefore, that's what makes this negative sign here. The force interactions between 1 and 3, on the other hand, are attractive, which means that F sub 13 is going to be to the right or positive. Now, substituting Coulomb's law in for each one of these terms, this becomes K times Q1, Q2 over the distance squared. I got to remember that that is negative. And then I'm going to add to that K, Q1, Q3 over the distance squared. Plugging in my values for K, I'm going to leave units out just this time to fit it all on the paper. 9 times 10 to the 9th. What the heck, I'll put them in there. Newton meters squared over Coulomb squared. And then I'm going to multiply that by Q1 and Q2. I've got to remember to keep my negative sign here and carry that. Q1 is 75 microcoulombs. So that's going to be 75 times 10 to the minus 6 in scientific notation, coulombs. And then I got to multiply that by 48 microcoulombs, or 48 times 10 to the minus 6 coulombs. And then divide all of that by the distance squared, which is going to be 0.35 meters. And I got to remember to square it. Now, I'm not done with the expression. I have to add to that the force interactions to the right, which is F13. So in the next line, I'll just do it down here. That becomes, again, 9 times 10 to the 9th Newton meters squared over Coulomb squared times 75 times 10 to the minus 6 coulombs times 85 times 10 to the minus 6 coulombs. Notice I've left out this negative sign here, and the reason is I've already taken into account the sign due to the direction of the forces here. So the negative sign that I put in here and the positive sign that I put in right here, taken into account those directions. Let's go ahead and remember to finish this guy up and divide by 0.35 meters squared. And when I add those two terms together, I get an answer, at least for the first one, of about negative 150 newtons, which means it's going to be to the left. In other words, the first term is larger than the second term. So I could say then that my force on charge number 1, the net force on charge number 1, due to the electric interactions with charges 2 and 3, is 150 newtons to the left. Now I can continue this and do it for the other charges, so let's go ahead and do that. Let's set up at least F sub 2. And if you notice, the forces acting on 2 due to 1, so F2 is going to be to the right. They're both positive, so 2 is going to be to the right. But also notice that F23 is also to the right because they're oppositely charged, but this guy here is on the right. So it gets attracted to it. So those are both going to be positive terms. That becomes F21 plus F23. And then I'm just going to basically plug in very similar terms. I'm going to go ahead and just start by putting them in. That's going to be 9 times 10 to the ninth. I'm going to write this in like I would on my calculator. So that's going to be 9E9, which is Coulomb's constant, times Q1, Q2 in this case, which is going to be 48 times 10 to the minus 6 coulombs. And I got to multiply that by 75, which is Q1, times 10 to the minus 6 coulombs. Divide that by 0.35 squared. And I'm going to add that to 9 times 10 to the ninth. By the way, I wrote this here in this way. This is kind of like TI calculator format. And it's what I would recommend putting into your calculators. There's so many numbers in scientific notation here that you're destined to make a mistake if you kind of don't do it that way. 48 times 10 to the minus 6, which is the charge of charge 2. And I'm going to multiply that by 85 times 10 to the minus 6, which is the charge of 3. So this is F23, and divide that again by 0.35 meters. And I got to remember to square that. And of course, I should get a net force now to the right. And when I do that, I get the net force on charge 2 is equal to 560 newtons. So now, 2/3 of the way through, I found the net force on 1, and I found the net force on 2. Let me go ahead and at least set up this last one, the net force on 3. So the interaction between 3 and 2 is going to be attractive. So that means that charge number 2 is going to be pulling this to the left. So F32 is to the left. And I could also say that the interaction between 3 and 1 is also to the left, F31. So both forces then should be negative in direction because they're pointing to the left. So that becomes negative F32 plus negative F31, or I can just write minus F31. And when I plug all those numbers into my calculator, I should get a negative, a net negative, or to the left, of 420 newtons. And that's my net force on charge number 3.